Okay, let's just start with a scene. You're in the chemistry lab,
Hmm?
and you open a bottle, and this very distinct sweetish smell fills the air.
Ah, yes, the classic fruity odor. That's diethyl ether for you.
Exactly. Now picture this. You have two test tubes. One has alcohol, say ethanol. The other one has this ether.
A classic comparison. I think I know where this is going.
You do. We take some of that bright purple liquid, acidified potassium permanganate.
Our favorite oxidizing agent, KMNO4.
We add a few drops of the alcohol, give it a little shake, and poof, the purple color is gone.
Reaction complete. Oxidation has occurred.
But then you go to the ether tube, you add the same purple drops, you shake it, you wait, and, well, nothing.
Nothing at all. The purple just stays there, stubbornly.
And that stubbornness is exactly what we're going to talk about today. We're doing a deep dive into Unit 7, alcohols, phenols, and ethers, focusing specifically on, well, ethers.
And this isn't just some minor topic. Understanding why ethers are so inert, so unreactive, that's their superpower. It's crucial for your Class 12 exams.
And it's not just about exams, right? This is about why we call ethers the solvents of choice in organic chemistry. We need liquids that can dissolve things without, messing up the entire reaction.
Correct. Without them, so many modern reactions would simply not be possible. They provide that safe, non-reactive environment for chemistry to happen.
So let's start with the absolute basics. What even is an ether?
At the simplest level, an ether is an organic compound where an oxygen atom is sitting between two carbon atoms.
So the basic structure is COC.
Exactly. Carbon, oxygen, carbon.
I want you to actually imagine this. Just close your eyes for a moment. Think about the oxygen atom. In water or alcohol, it's always connected to a hydrogen. It's sort of social. It has a hand free to wave.
For a reactive site.
Right. But in an ether, that oxygen is on vacation. It's hiding. It's sandwiched between two big carbon atoms.
That's a great way to put it. Now, if we look at what's really happening at the particle level,
Mm-hmm.
the general structure is ROR.
Where R is just some carbon chain?
Yes, an alkyl or even an aryl group. That central oxygen atom is SPA hybridized.
Okay, SPA, so that suggests a tetrahedral geometry, isn't it?
It does. But the CSC bond angle isn't the perfect 109.5 degrees. It's actually a bit wider, around 110 or 111 degrees.
That's interesting. Usually the lone pairs on the oxygen would squeeze the angle, like in water.
They do, but here you have two bulky R groups, the carbon chains. They push against each other, what we call steric hindrance, and that forces the angle to open up a little bit.
Okay, that makes sense. But the most important point here, the thing that changes everything, is what's missing.
Precisely. There is no hydrogen attached directly to the oxygen, and this is the key. It means ethers cannot act as hydrogen bond donors.
This brings us to the anchor definition for your exams. If you have to define it, what's the perfect line?
You should write, ethers are organic compounds with the general structure ROR, where oxygen is bonded to two carbon atoms. They are generally unreactive.
And this is where students often get confused. They see the oxygen and think.
They think, oh, it has oxygen just like alcohol, so it must react like alcohol.
But it doesn't.
No. That oxygen is shielded. It's protected. The CO bonds are strong. And without that reactive hydrogen, its chemistry is completely different.
I really like the analogy of the shy person.
Tell me more.
Well, an alcohol is like a person holding a friend's hand. That's the carbon. But their other hand, the hydrogen, is free and waving around. They're approachable, reactive.
Okay, I see that.
But in ether, the oxygen is a shy person sandwiched between two friends, one on the left and one on the right. Both hands are full. It's protected. It can't really interact with anyone else.
That maps perfectly onto its inertness. Its hands are full, so it can't react.
So why do ethers even exist? Why did chemistry need them?
Ah, that's a great question. It's because chemists needed a Goldilocks liquid.
Not too hot, not too cold.
Exactly. You see, hydrocarbons like petrol or hexane, they're nonpolar. They don't dissolve many things. Then you have alcohols. They are great solvents. They dissolve a lot, but they are too reactive. They have that OH group that interferes with many reactions.
So they mess things up.
Yes. The solution was ethers. They are just polar enough to dissolve a wide range of compounds, but they are inert enough to just sit back and watch the reaction happen without getting involved.
A bit of a historical note. They were used as anesthetics, weren't they? Diethyl ether.
That's right, in the 19th century. And it worked because it doesn't react chemically with your body. It just sort of physically interacts with nerve cells to cause sedation. It just sits there.
Let's guide our listeners through a mental movie now. Picture an oxygen atom.
Okay.
To its left, a carbon atom is bonded. To its right, another carbon atom.
The COC linkage.
Right. Now, visualize the oxygen's lone pairs of electrons. They're not pointing outwards, ready to react. They're sort of tucked inward between those two bulky carbon groups.
They're shielded.
Exactly. The whole structure looks sealed. It looks static. Nothing is waving. Nothing is exposed. And that's the picture you should have in your mind for why ethers are so stable.
And that picture directly explains the experiment we started with.
The purple test tube.
Yes, adding the acidified KMNO4. The reason alcohol reacts is because it has what we call an alpha hydrogen, and more importantly, the hydrogen on the oxygen itself. The oxidizing agent has a place to attack.
A handle to grab onto.
A perfect way to say it. But with ether, there's no such handle. The CO bond is too strong to break under these mild conditions, so the purple permanganate just floats around with nothing to do. It resists oxidation.
Let's talk about a technology application, something like THF.
Tetrahydrofuran, a very, very important ether, especially for Grignard reactions, which you will study in detail.
So what's the scenario here?
Grignard reagents are super reactive. They are like angry little molecules looking for a fight if you put them in a solvent like alcohol.
It's a disaster. The alcohol's hydrogen will immediately react and destroy the Grignard reagent.
Correct. So you need a bodyguard. You need a solvent that can dissolve the Grignard reagent but won't fight with it. That's where THF comes in.
It's an ether.
Yes. It's polar, so it dissolves the Grignard reagent perfectly, but it's inert. It acts like a bodyguard, keeping the reagent stable and ready for the main reaction, but never reacting with it itself.
Now here's a counterintuitive thought. A student might think.
Oxygen is very electronegative, so ethers must be very reactive.
Exactly. It seems logical, but the reality is different.
The reality is they are polar, yes, but they are inert. And the reason is subtle.
Go on.
They can accept a hydrogen bond. That's why they're slightly soluble in water. The lone pairs on the ether's oxygen can be attracted to a hydrogen from a water molecule.
But they can't donate one.
They cannot donate one because they don't have a hydrogen on the oxygen. This unique property polarity without the reactivity of a donor is what makes them so special.
Okay, this is all fantastic. But for a student facing an exam, they need the exact lines to write to get full marks. Could you give us those key exam-safe clarity lines?
Of course. Let's go through them slowly. First, on structure.
What should they write?
Ethers have the general structure ROR. The oxygen is bonded to 2 carbon atoms. Simple and direct.
Okay. What about the bond angle?
The COC bond angle is approximately 110 degrees, similar to water due to spot hybridization. You can add that it's slightly larger due to steric repulsion if you want to impress.
Good tip. Now, the most important part. Reactivity.
For reactivity, you must state, ethers are generally unreactive toward nucleophilic substitution and oxidizing agents. This makes them ideal solvents.
That's the core message. And what about hydrogen bonding?
You have to be very clear here. Ethers do not have a hydrogen bonded to oxygen. They cannot form hydrogen bonds as donors.
And one last point, to compare them with alcohols.
Ethers lack the reactive alpha hydrogen found in alcohols, preventing oxidation under mild conditions. That explains our purple test tube experiment perfectly.
Perfect. Let's do a quick summary of this entire session for revision.
Let's.
The core idea. Ethers are COC. The oxygen is protected, it's sandwiched. The analogy to remember is the shy person holding hands with 2 friends, the 2 carbons, so they can't interact with anyone else.
A very effective image.
For an example, always think of THF or diethyl ether being used as the inert solvent, the bodyguard for Grignard reagents.
Yes, that is a prime application.
And the most critical exam key, remember they are inert or unreactive because that central oxygen is protected and crucially, it lacks a hydrogen atom.
That's it. My final piece of advice for any student is this. If you see an ether in an exam question, your first thought should be solvent or unreactive. Don't try to make it react like an alcohol. That's the trap.
Great advice. And to our listeners, thank you for joining this deep dive. Next time you see the chapter on ethers in your textbook, I hope you visualize that sandwiched oxygen.
My pleasure. Good luck to all the students.
We'll catch you in the next one.